Chapter 7. How we imagine things might go wrong. The rapid progress we've witnessed in AI since the turn of the century has led to a lot of press coverage. Some of this coverage is balanced and reasonable. Much of it is frankly rather silly. Some of it is informative and constructive. Much of it is nothing more than scaremongering. In July 2017, for example, it was widely reported that Facebook had closed down 2 AI systems after they had begun to converse in their own made-up language, which was apparently incomprehensible to their designers. The clear implication in headlines and social media postings at the time was that Facebook shut down the systems because they were afraid they were losing control. In fact, the Facebook experiment was completely routine and totally harmless. It was the kind of experiment that a student might undertake as a project. There was no more possibility of the Facebook systems running amok than there is of your toaster transforming itself into a killer robot. It was, simply, impossible. While on the one hand I found coverage of the Facebook incident rather comical, it also left me deeply frustrated. The problem is, reporting of this kind panders to the Terminator narrative of AI, that we are creating something we won't be able to control, which could pose an existential risk to humanity. You can almost hear a voiceover from Arnold Schwarzenegger in his classic role. This narrative still dominates the debate about the future of AI, which is now routinely discussed in tones previously reserved for nuclear weapons. Elon Musk, the billionaire entrepreneur and co-founder of PayPal and Tesla, was sufficiently worried by this idea that he made a series of public statements expressing his concerns and donated $10 million research funding to support responsible AI. In 2014, Stephen Hawking, then the world's most famous scientist, publicly stated that he feared AI represented an existential threat to humanity. The Terminator narrative is damaging, for several reasons. First, it makes us worry about things that we probably don't need to fret about. But secondly, it draws attention away from those issues raised by AI that we should be concerned about. These may not make as good headlines as the Terminator, but they are probably the issues that we should be concerned about now. So, in this chapter, I want to address the headline fears about AI, the possibility of Terminator scenarios, and how AI might go wrong. I will start in the next section by tackling this narrative head-on. We'll discuss how it might happen and how likely it is. This then leads us to a discussion of ethical AI, the possibility of AI systems acting as moral agents, and the various frameworks for ethical AI that have been proposed. I'll conclude by drawing attention to one particular feature of AI systems in which they are prone to failure, albeit not at a highly scary level. If we want an AI system to act on our behalf, then we need to communicate to it what we want. But this turns out to be hard to do, and if we don't take care when communicating our desires, then we may get what we asked for, but not what we actually wanted. Terminating the Terminator. In contemporary AI, the Terminator narrative is most commonly associated with an idea called the singularity, which was introduced by the American futurologist Ray Kurzweil. In his 2005 book, The Singularity is Near, he wrote, "The key idea underlying the impending singularity is that the pace of change of our human-created technology is accelerating and its powers are expanding at an exponential pace. Within several decades, information-based technologies will encompass all human knowledge and proficiency, ultimately including the pattern recognition powers, problem-solving skills, and emotional and moral intelligence of the human brain itself." Although Kurzweil's vision of the singularity is quite broad, the term has come to be identified with one specific idea. The singularity is the hypothesized point at which computer intelligence, in the general sense, exceeds that of humans. At this point, it is suggested, computers could start to apply their own intelligence to improving themselves, and this process will then start to feed off itself. After that, these improved machines will then apply their improved intelligence to improving themselves further, and so on. From that point on, so the argument goes, it will be impossible for mere human intelligence to regain control. It's a very compelling idea, and a deeply alarming one. But let's pause for a moment to examine the logic behind the singularity. In a nutshell, Kurzweil's main argument hinges on the idea that computer hardware, processors, and memory is developing at such a rate that the information processing capacity of computers will soon exceed that of the human brain. His argument derives from a well-known dictum in computing called Moore's Law, named after Gordon Moore, a co-founder of Intel, who formulated it in the mid-1960s. Moore's Law states that the number of transistors that can fit on a fixed area of a semiconductor doubles about every 18 months. The practical upshot of Moore's Law is that, to put it crudely, computer processors can be expected to roughly double in power every 18 months. Moore's Law has several important corollaries. Among them is that computer processing power could be expected to get progressively cheaper at the same rate, and that processors themselves to get progressively smaller. Moore's Law proved very reliable for nearly 50 years, although some current processor technologies started to hit the physical limits of their capabilities around 2010. Now, Kurzweil's argument implicitly links the inevitability of the singularity to the availability of raw computer power implied by Moore's Law. But this link is dubious. Indulge me for a moment with a thought experiment. Imagine that we could download your brain into a computer. We're in the realm of pure fantasy here, of course. And suppose the computer we download your brain to is the fastest, most powerful computer ever. With all this amazing processing power at your command, would you be super intelligent? For sure, you'd be able to think quickly, but does that make you more intelligent? In some trivial sense, I guess it does, but not in any meaningful sense of intelligence, and not in the sense of the singularity. Raw computer processing power, in other words, will not inevitably lead to the singularity. It is probably a necessary requirement for it. We won't achieve human-level intelligence without highly powered computers, but it isn't a sufficient requirement. Simply having highly powered computers won't get us to human-level intelligence. To put it another way, AI software, machine learning programs, for example, improves at a much, much slower pace than the hardware. There are other reasons to doubt whether the singularity is in prospect. For one thing, even if AI systems did become as intelligent as people, it does not follow that they would be able to improve themselves at some rate beyond our ability to understand. As this book has shown, we have made only rather slow progress on AI over the past 60 years. What evidence is there that human-level general AI will be able to make AI progress faster? A related argument concerns the idea of AI systems working with each other together to achieve intelligence beyond our ability to comprehend or control it. Compare with the Facebook incident I mentioned at the start of the chapter. But I don't find this argument very convincing either. Suppose you got together 1,000 clones of Einstein. Would their collective intelligence be 1,000 times that of Einstein? In fact, I suspect their collective intelligence would be considerably less than that. Again, although our 1,000 Einsteins would be able to collectively do some things faster than one Einstein could, that isn't the same as being smarter. For these reasons and more, many AI researchers are skeptical about the singularity, at least for the foreseeable future. We know of no path that will take us from where we are now, in terms of computing and AI technology, to the singularity. But some serious commentators are still worried and claim these arguments are complacency. They point to the experience of nuclear energy. Back in the early 1930s, scientists knew that there was a huge amount of energy locked in the nuclei of atoms, but had no idea how to release it, or even if that was possible. Some scientists were extremely dismissive of the idea that nuclear energy could be harnessed. Lord Rutherford, one of the most famous scientists of his age, said it was moonshine to imagine that we would be able to tap into this energy source. But famously, the day after Rutherford dismissed the possibility of nuclear energy, the physicist Leo Szilard was crossing a road in London, mulling over Rutherford's pronouncement, when the idea of a nuclear chain reaction suddenly occurred to him. Just over a decade later, 2 Japanese cities were destroyed by bombs powered in the way that Szilard had imagined in a split second. Could there be a Leo Szilard moment in AI, a sudden insight that would quickly take us to the singularity? Of course, we can't rule it out, but it is highly unlikely. A nuclear chain reaction is actually a very simple mechanism. A high school student can understand it. All the experience of AI research over the last 60 years tells us that human-level AI is not. But what about the distant future, 100 years ahead or 1,000? Here, I have to admit that things are much less clear. It would be unwise to try to predict what computer technology will be capable of in 100 years, still less 1,000. But it seems highly unlikely to me that if the singularity occurs, it will take us by surprise, as in the Terminator narrative. To use an analogy by Rodney Brooks, think of human-level intelligence as a Boeing 747. Is it likely that we would invent a Boeing 747 by accident, or that we would develop a Boeing 747 without expecting to? A counter-response is that although it might be unlikely, the consequences for us all if it did occur would be so dramatic that this justifies thinking and planning ahead for the singularity now. We need to talk about Asimov. Whenever I discuss the Terminator narrative with a lay audience, somebody suggests that what we need are something like the 3 laws of robotics, formulated by the renowned science fiction author Isaac Asimov. The 3 laws were invented by Asimov in a series of stories about robots equipped with a version of strong AI via what he called positronic brains. Asimov first formulated the laws in 1939, and over the next 4 decades they provided him with an ingenious plot device for what would ultimately become a celebrated series of short stories and a disappointing Hollywood movie. The science of the AI in Asimov's stories, positronic brains, is meaningless, although of course the stories are nonetheless entertaining for that. What is interesting for our purposes are the laws themselves. 1. A robot may not injure a human, or through inaction allow a human to come to harm. 2. A robot must obey orders given by humans except where they would conflict with the first law. 3. A robot must protect its own existence as long as this does not conflict with the first or second laws. The laws are beautifully formulated, and at first sight appear to be ingeniously robust. Could we design AI systems with these laws built in? Well, the first thing to say about Asimov's laws is that, ingenious though they are, many of Asimov's stories were based upon situations in which the laws turned out to be flawed or led to contradictions. In the story Runaround, for example, a robot called SPD-13 seems destined to endlessly circle a pool of molten selenium because of a conflict between the need to obey an order, the second law, and the need to protect itself, the third law. It orbits the pool at a fixed distance because if it gets any closer, the need to protect itself kicks in, while if it gets any farther away, the need to obey kicks in. There are many other examples in his stories, and if you haven't done so already, I urge you to read them. So, the laws themselves, ingenious as they are, certainly aren't by any means watertight. But the bigger problem with Asimov's laws is that implementing them within an AI system just isn't feasible. Think about what it would mean to implement the first law, for example. Every time an AI system was contemplating an action, it would need to consider the effects that this action might have, presumably, on all humans, or is it only some that matter? And into the future, too, or do you only care about the here and now? This is not feasible. And the "or through inaction" clause is equally problematic. Should a system constantly contemplate all its possible actions with respect to every person to see whether the relevant action prevents harm? Again, it just won't work. Even capturing the notion of harm is difficult. Consider, when you fly on a plane from London to Los Angeles, you are consuming a large amount of natural resources and generating a lot of pollution and carbon dioxide along the way. This is almost certainly harming someone, but in such a way that it is impossible to precisely quantify it. A robot that obeyed Asimov's laws literally would not, I think, be persuaded onto an airplane or into an automobile.
Actually, I doubt it would be able to do very much at all. It would likely be huddled in a corner somewhere, hiding from the world, crippled by indecision.
So, if Asimov's laws and other well-intentioned systems of ethical principles for AI don't necessarily help us, how should we think about the acceptable behavior of AI systems? We need to stop talking about the trolley problem. Asimov's laws can be seen as the first and most famous attempt to formulate an overarching framework to govern decision-making in AI systems. Although it wasn't intended as a serious ethical framework for AI, we can see it as the ancestor of a whole host of such frameworks that have appeared alongside the recent growth of AI and have been the subject of serious research. In the remainder of this chapter, we will survey this work and discuss whether or not it is heading in the right direction. We'll begin our survey with one particular scenario that has attracted more attention in the ethical AI community than perhaps any other. The trolley problem is a thought experiment in the philosophy of ethics, originally introduced by British philosopher Philippa Foot in the late 1960s. Her aim in introducing the trolley problem was to disentangle some of the highly emotive issues surrounding the morality of abortion. There are many versions of Foot's trolley problem, but the most common version goes something like this. See Figure 14 in the accompanying document. A trolley, i.e. a tram, has gone out of control and is careering at high speed toward 5 people who are unable to move. There is a lever by the track. If you pull the lever, then the trolley will be diverted down an alternative track, where there is just one person who also cannot move. If you pull the lever, then this person would be killed, but the 5 others would be saved. Should you pull the lever or not? The trolley problem has risen rapidly in prominence recently because of the imminent arrival of driverless cars. Pundits were quick to point out that driverless cars might find themselves in a situation like the trolley problem, and AI software would then be called upon to make an impossible choice. "Self-driving cars are already deciding who to kill," ran one internet headline in 2016. There was a flurry of anguished online debate, and several philosophers of my acquaintance were surprised and flattered to discover that there was suddenly an attentive audience for their opinions on what had hitherto been a rather obscure problem in the philosophy of ethics. Despite its apparent simplicity, the trolley problem raises some surprisingly complex issues. My intuitive response to the problem is, all other things being equal, I would pull the lever because it would be better to have just one person die rather than 5. Philosophers call this kind of reasoning consequentialist because it assesses the morality of actions on the basis of their consequences. The best-known consequentialist theory is utilitarianism. It has its origins in the work of 18th-century British philosopher Jeremy Bentham and his student John Stuart Mill. They formulated an idea called the greatest happiness principle, which, speaking approximately, says that one should choose whichever action maximizes the aggregate happiness of the world. While the general principle seems appealing, making the idea of the aggregate happiness of the world precise is not easy. For example, suppose the 5 individuals in the trolley problem are evil mass murderers, while the other individual is an innocent young child. Do the lives of 5 evil mass murderers outweigh that of an innocent young child? If not 5, Suppose there were 10 mass murderers. Would that be enough for you to decide to pull the lever and save the killers at the expense of a child's life? An alternative point of view is that an action is acceptable if it is consistent with some general good principle, the standard example being that taking life is wrong. If you adhere to the principle that taking life is wrong, then any action that causes a death would be unacceptable. Someone who accepted such a principle would not take action in response to the trolley problem, since their action would cause someone's death, even though not acting leads to 5 other deaths. A third standpoint is based on the idea of virtue ethics. From this standpoint, we might identify a virtuous person who embodies the virtues that we aspire to in a decision-maker, and then say that the correct choice is the choice that would be made by this sort of person in this setting. Of course, in AI, the decision-maker would be an agent, a driverless car, which must choose between driving straight ahead and killing 5 people, or swerving and killing 1. So, what would and what should an AI agent do when faced with a trolley problem or something like it? Well, first of all, we should ask ourselves whether it is reasonable to expect more of an AI system than we would expect of a person in a situation like this. If the greatest philosophical thinkers in the world cannot definitively resolve the trolley problem, then is it reasonable of us to expect an AI system to do so? Secondly, I should point out that I have been driving cars for decades, and in all that time I have never faced a trolley problem, nor has anyone else I know. Moreover, what I know about ethics and the ethics of the trolley problem is roughly what you heard earlier. I wasn't required to pass an ethics exam to get my driver's license. This has not been a problem for me so far. Driving a car does not require deep ethical reasoning. So requiring that driverless cars can resolve the trolley problem before we put them on the roads therefore seems to me a little absurd. Thirdly, the truth is that however obvious the answers to ethical problems might seem to you, other people will have different answers, which seem just as self-evident to them. Intriguing and ingenious though it undoubtedly is, the trolley problem does not, I think, have much of value to tell us about AI software for driverless cars. I don't believe that the driverless cars we are likely to encounter in the coming decades will do ethical reasoning of this type. So, what would a real driverless car do in practice when faced with a situation like the trolley problem? The likeliest outcome would be that the car would just slam on the brakes, and perhaps in practice, that is probably all that we would manage to do in the same situation. The rise of ethical AI. Of course, there are much wider issues around AI and ethics, which are perhaps of more immediate importance and relevance than the arguably rather artificial trolley problem, and at the time of writing, these issues are being keenly debated. Every technology company, it seems, wants to demonstrate that their AI is more ethical than everyone else's. Scarcely a week goes by without a press release announcing a new ethical AI initiative. It is worth reflecting on these a little and the role they are likely to play in how AI develops in the years to come. One of the first and most influential frameworks for ethical AI was the Asilomar Principles, which were formulated by a group of AI scientists and commentators who met in the Californian resort of the same name in 2015 and 2017. The main deliverable was a set of 23 principles, which AI scientists and developers across the world were asked to ascribe to. Most of the Asilomar principles are pretty uncontentious. The first is that the goal of AI research should be to create beneficial intelligence. The sixth is that AI systems should be safe and secure. And the 12th is that people should have the right to access, manage, and control data that relates to them. Some of the principles, however, seem rather aspirational. The 15th, for example, requires that the economic prosperity created by AI should be shared broadly to benefit all of humanity. I personally have no difficulty in ascribing to this principle, but I'm afraid I think it is naive to imagine that big business will do anything more than pay lip service to it. Big businesses are investing in AI because they hope it will give them a competitive advantage that will deliver benefits to their shareholders, not because they want to benefit humanity. In the interests of transparency, I should point out that I was invited to both of the meetings that led to the Asiloma Principles. And I would have loved to have gone. As it happens, on both occasions, prior commitments got in the way. The final 5 principles relate to the long-term future of AI. Capability caution. There being no consensus, we should avoid strong assumptions regarding upper limits on future AI capabilities. Importance. Advanced AI could represent a profound change in the history of life on Earth and should be planned for and managed with commensurate care and resources. Risks. Risks posed by AI systems, especially catastrophic or existential risks, must be subject to planning and mitigation efforts commensurate with their expected impact. Recursive self-improvement. AI systems designed to recursively self-improve automatically improve their intelligence and then use their improved intelligence to improve themselves further, or self-replicate in a manner that could lead to rapidly increasing quality or quantity, must be subject to strict safety and control measures. Common good. Superintelligence should only be developed in the service of widely shared ethical ideals and for the benefit of all humanity, rather than one state or organization. Again, I have no difficulty at all in ascribing to these principles, but we are so far from the scenarios hinted at here becoming a reality that including them almost amounts to scaremongering. Maybe these issues will be worth losing sleep over at some point in the future, but to give them prominence now presents a misleading picture of where AI is, and more worryingly, distracts us from the problems that we should be concerned about, which we will discuss in the next chapter. Of course, because the scenarios indicated here are likely to be a long way in the future, it doesn't cost companies anything to sign up to them, and it makes for good publicity. In 2018, Google released their own guidelines for ethical AI. Somewhat pithier than the Asiloma Principles, they cover much of the same territory, being beneficial, avoiding bias, being safe, and, helpfully, Google also provided some concrete guidance around best practice in AI and machine learning development. Another framework was proposed by the European Union at the end of 2018, and yet another by the IEEE, a key professional organization for computing and IT. Many major companies, and not just IT companies, have also released ethical AI guidelines of their own. It is, of course, wonderful that big businesses are declaring their commitment to ethical AI. The difficulty, though, is understanding precisely what they have committed to. High-level aspirations, such as sharing the benefits of AI, are welcome, but translating that into specific actions is not easy. The company motto used by Google for more than a decade was, "Don't be evil." What precisely does that mean for Google's employees? They need much more specific guidance if they are to prevent Google from crossing over to the dark side. Within the various frameworks that have been proposed, certain themes recur, and there is increasing consensus around these. My colleague, Virginia Dignam, at Umeå University in Sweden, has championed these issues, and she distills them into 3 key concepts: accountability, responsibility, and transparency. Accountability, in this sense, means that, for example, if an AI system makes a decision that significantly affects someone, then they have a right to an explanation for that decision. But what counts as an explanation is a difficult issue, one which will have different answers in different settings, and current machine learning systems are not capable of providing explanations. Responsibility means that it should always be clear who is responsible for a decision, and, crucially, that we should not try to claim that an AI system was responsible for a decision. The responsible party will be individuals or organizations that deployed the system. This points toward a deeper philosophical issue, one relating to the question of moral agency. A moral agent is commonly understood to be an entity that is capable of distinguishing right and wrong, and of understanding the consequences of their actions with respect to such distinctions.
It is often imagined in popular discussion that AI systems are or can be moral agents and can be held accountable for their actions.
The general view in the AI community is that this is not the case. Software can't be held responsible. Rather, responsibility must lie with those that develop and deploy the technology. More generally, responsibility in AI doesn't imply building machines that are themselves morally responsible, but rather developing AI systems in a responsible way. For example, distributing a Siri-like software agent that misled users into believing that they were interacting with another person would be an irresponsible use of AI by the developers of it. The software isn't culpable here, those who develop and deploy it are. Responsible design here would mean that the AI would always make it clear that it is non-human. Finally, transparency means that the data that a system uses about us should be available to us, and the algorithms used within that should be made clear to us too. Be careful what you wish for. The discussion of ethical AI sometimes makes us forget one of the more mundane realities about how things might go wrong. AI software is, well, software, and we don't need any fancy new technologies for software to go wrong. The problem of developing bug-free software is a huge research area in computing. Finding and eliminating bugs is one of the main activities in software development. But AI provides novel new ways for bugs to be introduced. One of the most important of these arises from the fact that if AI software is to work on our behalf, then we need to tell it what we want it to do. And this is often not nearly as easy as it might appear. About 15 years ago, I was working on techniques intended to enable vehicles to coordinate themselves without human intervention. The particular scenario I was working on was a railway network. This makes it sound much more impressive than it actually was, because the network I was looking at consisted of 2 trains travelling in opposite directions on a circular railway. And they were virtual trains. No actual railway track was involved. Not even a toy railway track, actually. At one point, the pretend railway passed through a narrow tunnel, and if ever both trains entered the tunnel at the same time, then there would be a simulated crash. My goal was to prevent this. I was trying to develop a general framework that would allow me to present a goal to my system, the goal in this case being to prevent a crash, so that the system would come back with some rules that, if the trains followed them, would be guaranteed to ensure that my goal was achieved. The trains wouldn't crash. My system worked, but not in the way I had in mind. The first time I presented my goal, the system came back with the following recommendation. Both trains must remain stationary. Well, of course, this works. If both trains remain stationary, then no crash will occur. But it wasn't the kind of solution I was after. The problem I encountered is a standard one in AI, and indeed in computer science generally. The problem is this. We want to communicate our desires to a computer so that the computer can pursue them on our behalf. But communicating our desires to a computer is a deeply problematic process for several reasons. First of all, we may ourselves not know what we actually want, at least not explicitly, and in this case, articulating our desires is going to be impossible. Often our desires will be contradictory, in which case, how is an AI system to make sense of them? Moreover, it may be impossible to spell out our preferences in toto, so the best we will often be able to do is give a snapshot of our preferences, leaving gaps in the overall picture. How, then, should the AI system fill in the gaps? But finally, and perhaps most important, when we communicate with people, we usually assume that we share common values and norms. We don't explicitly spell these out every time we interact. But an AI system doesn't know about these values and norms. So they either have to be explicitly spelled out, or else we somehow have to make sure that the AI system has them in the background. If they aren't there, then we may not get what we really wanted. In the train scenario, I communicated my goal that the trains were to avoid crashing, but forgot to convey that they should still be allowed to move. I had forgotten that although a human would almost certainly implicitly understand that this was my intention, a computer system would not. Scenarios like this were popularized by Oxford philosopher Nick Bostrom in his best-selling 2014 book, Superintelligence. He calls this perverse instantiation. The computer does what you asked for, but not in the way you anticipated. Hours of fun are to be had dreaming up other perverse instantiation scenarios. You ask a robot to prevent deaths from cancer, so it murders everyone, and so on. Of course, this is a problem that we encounter repeatedly in everyday life. Whenever someone designs a system of incentives that are intended to encourage a certain behavior, someone else will find a way to game the system, gaining the rewards without behaving as intended. I am reminded of a possibly apocryphal story from the era of Soviet Russia. The Russian government wanted to incentivize the production of cutlery, and so decided to reward factories that produced cutlery according to the weight of cutlery they produced. What happened? Cutlery factories quickly started to produce very heavy cutlery. Aficionados of classic Disney films may recognize a closely related type of problem. The 1940 Disney film Fantasia features a segment in which a naive young sorcerer's apprentice, Mickey Mouse, becomes tired of his chore of carrying water into the house from a well. To relieve himself of the burden, he brings a broomstick to life to do this for him. But Mickey dozes off, and upon waking up, his attempts to stop the broomstick bringing in water, bucket after bucket, result in ever more magical broomsticks flooding his basement. It requires the intervention of his master, the sorcerer, to rectify the problem. Mickey got what he asked for, but not what he wanted. Bostrom also considered these types of scenarios. He imagined an AI system that controlled the manufacture of paperclips. The system is given the goal of maximizing the production of paperclips, which it takes literally, transforming first the Earth and then the rest of the universe into paperclips. Again, the problem is ultimately one of communication. In this case, when we communicate our goal, we need to be sure that acceptable boundaries are understood. The challenge in all these scenarios is for the computer to understand what it is we really want. The field of inverse reinforcement learning is directed at this problem. We saw regular reinforcement learning in Chapter 5. An agent acts in some environment and receives a reward. The learning challenge is to find a course of actions that maximize the reward received. In inverse reinforcement learning, we instead get to see ideal behavior, what a person would do. The challenge is then to figure out what the relevant rewards are for the AI software. In short, the idea is to look at human behavior as our model for desirable behavior.